Hello everyone, Manyepa here, and I'm about to go through working out solutions to the 2020 Science Paper 1, which is Physics 5124. So in this video, I'm just going to look at Section B questions. I'm just going to answer Section B questions. So we get to Section B. Where is it? Section B. There it is. So straight away we go to section B, question B1, which is our first question in section B. Figure B 1.1 below shows a simple pendulum suspended from a fixed point. The probe is slightly put to position A and then released. State one factor that does not affect the period of a pendulum: the mass of the bulb. Simple pendulums are not affected by the mass of the bulb, and also the angle of displacement. What affects the period of a pendulum is the length of the pendulum, which is from this point here to the center of the bulb, and also the value of the gravitational field, therefore the acceleration due to gravity, or the value of g. Question B. If the values of time for 20 oscillations obtained were 16.1, 15.9, 16.0, 16.2, and 15.8, calculate the period of a pendulum. The formula for period is this: time over number of oscillations. So in this question, what is implied is that the first time 20 oscillations took 16.1 seconds. The second time 20 oscillations took 15.9 seconds. The third time 20 oscillations took 16.0. So to find the average time, I added all of them, then divided by 5, because there are 5 runs. Therefore 1, 2, 3, 4, and 5. So my average time is 16.0. So I plug in my time here, then the number of oscillations 20, which is this, and it gives me 0.8 as my period. Question C. Calculate the frequency of the pendulum. I actually made some errors there, but I'm sure you're able to see. Frequency is equals to number of oscillations over time taken. If the oscillation is 1, then the time taken is going to be equal to the period of that oscillation. Therefore, frequency may be frequency is equal to, if the oscillation is 1, you no need of writing n there, just write 1 over period. So this applies only when you're given one cycle. If the number of cycles or the oscillations are many, you use this one, and then this one becomes the period of time that it took for those oscillations to run. So my frequency is 1.25 per second, which is also expressed as 1.25 Hz. I flip to the next part. Next question. A car of mass 900 grams. A car has a mass of 900 grams. It accelerates from rest at a rate of 1.2 meters per second. Calculate the time taken to reach a velocity of 30 meters per second. We are told that this car accelerates from rest. Therefore, I have chosen this equation because there are a number of equations of motion, but I've chosen this one because it has got the variables that fit with my question. So as you choose your equation of motion, you have to know what you are calculating for, and you have to know what you have, what has been given, and what can easily be found from the question given. So here I have my final velocity. The car started from rest, that's my initial velocity. Acceleration is this value, and hence time can be calculated. I simply write my equation, and eventually I make t the subject, where I'm having t is equals to v minus u over a. V is my final velocity, u is my initial velocity. So 30 minus 0, because starting from rest meaning it wasn't moving, therefore velocity was 0. So I have 30 minus 0 over 1.2, and the answer comes out as 25 seconds. Therefore, the time taken to reach velocity of 30 meters per second will be 25 seconds. The next question there is force required to accelerate the car at the rate of 1.2 meters per second squared. Therefore, from Newton's second law of motion, force is going to be equal to mass times acceleration. The acceleration is given, the mass is also given in the question here as 900. So the force is simply going to be 1000 80 newtons. That's going to be the force. If you're given any opposing force, and you are supposed to find the resultant force, but that will be our force there. I go to question B3, therefore question 3 of section B. There's a wheelbarrow there. There's a simple machine. So below is a diagram showing a load being moved using a wheelbarrow. Okay, and that's our diagram there. The total mass of the wheelbarrow and the load is 80 kgs, kilograms. And G, which is the gravitational constant, is 10, taken to be 10. The first question is calculate the weight of the wheelbarrow and the load. The formula used, of course, is weight is equals to mass times the gravitational constant. Therefore, the mass of the wheelbarrow is 80 kgs, which is this 80. The constant is 10, which is this 10, giving us 800 newtons. The weight of the wheelbarrow and the load is 800 newtons together. So when you'll be lifting this wheelbarrow, you actually be working against, or you'll be lifting 800 newtons. Question A2, force F required to lift the wheelbarrow. In our diagram, we're having this force F here. So what minimum force would you apply or would be needed to lift the wheelbarrow? So force F, I use my principle of moments, principle of moments, where I express it like this, clockwise against anti-clockwise. Therefore, my 800 newtons is my clockwise times the distance of this 800 newtons from the pivot, which is 0.5 meters. Therefore, on my diagram here, my pivot is here, which is my turning point, and the weight of the wheelbarrow is acting along this line here. That's where the center of gravity is, or center of mass. Let me just say center of gravity is. That's the point where the mass of the wheelbarrow, the weight of the wheelbarrow, is acting from. Therefore, this creates a clockwise moment at this point here. Okay, so this is my clockwise moment, and it's acting at 0.5 meters away from the pivot. And then this, from this point to here, is going to give me my anti-clockwise or anti-clockwise moment, where I'll have the distance, which is going to be 0.5 plus 1.5 multiplied by F. So coming back to my calculation here, I've already done that. So 800 times 0.5 is equals to F times 2. This 2 meters is coming from, of course, the 0.5 plus 1.5, giving us 2 meters. And then we make F the subject, resultantly giving us a force of 200 newtons there. So force F would have a value of 200 newtons. B, state whether force F will increase or reduce when the handle of the wheelbarrow handles are made longer. Force F would reduce. Force F would reduce because the moment is calculated by multiplying the distance times the force. Okay, distance times force, which is this distance times force. So if you increase the distance and then you multiply with the constant force 200, of course, increase in the distance will actually result into a much larger, will result into a much lesser F. Okay. Remember the formula for moment, a single moment, is M is equals to FD. Okay, so if you increase the distance, then the moment remains constant. Okay, therefore at the moment when you'll be calculating for F, you're going to have M, which will be constant, and D, which would have increased. So the ultimate answer would be smaller. The force would reduce. The force would reduce. Yeah, hopefully you're able to see my angle of explanation there. My next question there is question 4. Below is a diagram showing a stone of mass 2 kgs that was pushed up a slope. The stone is being pushed from Q to R, and it goes on to say 72 joules of work was done in moving the stone up the slope from Q to R. What is the potential energy of the stone at R? There is our R up there. Remember, the amount of work done is equivalent to the energy expended. Whenever energy is converted from one form to another, work is done. Therefore, you cannot do work without energy. That is why energy is defined as the ability to do work. When energy is not being converted to any form, then work is not being done. So the moment you do work, and you expend this much energy to push the stone up, that will be the amount of energy that the stone will be gaining each time you push it up. Okay, so the amount of potential energy will be equal to the amount of work done in pushing the stone up. So 72 joules of work is done when moving the stone up. Therefore, that is the amount of energy that the stone will also gain. So the stone will actually gain 72 joules. Question B. If the stone falls from side RT, what would its potential energy be at S, the midpoint of its fall? Therefore, we have our S there. Therefore, the height here is half, of course, and the energy would also half. Okay, let's just get back to the calculation and try to explain. Gravitational potential energy, or just potential energy, is equals to 72. Up there, the potential energy is equal to 72. Therefore, as the stone is falling, at the exact instant when the stone reaches S, it's going to have half the amount of energy that it was having when it was up here. Okay, so it's going to have half the amount of energy. Therefore, the amount of energy is going to be 36 joules, because the height has been halved. The height has been halved. Okay. C. Calculate the height TR. Potential energy is equals to mass times gravity times height. Mg, remember, weight is equals to mass times gravity. Therefore, this is the same as weight. Therefore, potential energy is equals to weight times height. Weight of what? Weight of the object that is at that height. Therefore, the total amount of potential energy is 72, and the weight of the object is 20. Remember, the stone is 2 kgs. The stone is 2 kgs. So 20 times 10, which is mass is 2, gravitational force is 10, so it gives you 20 times height. Then you make h the subject and divide by 22 divided by 20, giving you 3.6 meters. Therefore, the height TR, which is this TR, is actually 3.6 meters. 3.6 meters. Question C2. Velocity of the stone just before it strikes the ground. This formula here is used to determine velocity of a freely falling object. You can use any other equation of motion that would give you the same answer, but I usually go for this one because it's easy to remember. So that's our formula there. V is equals to root 2gh. Gravitational field strength, the height, then 2 is the constant. So 2 is our constant, 10 is the gravitational field, which is 10, and then the height is 3.2. Therefore, the stone would simply be falling with a velocity of this much when it falls through this height. So velocity of the stone just before it strikes the ground, therefore it would fall through the whole lot of this height, which is 3.6 meters, and just before it hits the ground, therefore the velocity it would be 8.49 meters per second, or 8.5 if you like. Question B5. Diagram below is a diagram showing a wave traveling along a spring in the direction shown. We have our spring here and the wave is moving that way. In what way is this wave the same as the sound wave? You look at how the wave is progressing. This is more like a spring which is bouncing. It's not bouncing vertically but horizontally, and then its bouncing is back and forth. Therefore, it is a longitudinal wave, just like the way our sound also bounces. Sound is produced by speakers which also vibrate back and forth. Therefore, it is a longitudinal wave. That's the similarity between this kind of bouncing or movement or wave with a sound wave. Second question there, B. What are regions U and W called? You look at the wave there. This is a compression. The spring here is compressed. The waves or the rings are simply close to each other. This is the rarefaction. The waves are stretched or spaced. Therefore, U is a compression, W is a rarefaction. Yeah. Number C. Explain why sound waves travel faster in liquids than in gases. The answer here, my explanation would be because liquids are more denser, thus vibrations are passed on at a higher rate or faster rate than in gases. Sound is a mechanical wave, so it has to pass through matter. So the more matter you have, the more particles you have that are going to vibrate to the wave and pass it on. So the faster the sound. Air is spaced. liquids are much densely packed compared to gases. The question ends there. We'll go to the next question. A ray of light travels from air into water at an angle of 40 degrees between the normal and the incident ray. If this ray produces an angle of refraction of 29 degrees, calculate 1. The refractive index of water. So to make this drawing, sometimes you can scribble down a drawing for you to simply think properly. This is my normal, though it's not dotted, but that's my normal. An imaginary line which is drawn at right angle to the interface at the point passing through the point of incidence, and this line is there, or is used to measure. It's a reference point when you're measuring the angle of incidence and angle of refraction. So the ray is said to fall at 40 degrees, okay, to the incident ray between the normal. Therefore, this angle is 40 degrees, and then this angle of refraction is 29 degrees. Air, water. When a ray of light is moving from a less dense material to a more dense material, it bends towards the normal. That is why this is greater than this one here. So do not be interfered by angles on a straight line. Therefore, formula for calculation of the refractive index is here. Refractive index is equal to sine I, which is sine of the angle of incidence, over sine R, which is the sine of the angle of refraction. Sine I is 40 over sine R. Therefore, we have those values. And finally, the refractive index is, rounding it off, is 1.33. That will be the refractive index of water. Okay. Question 2, the critical angle of water. The critical angle of water. What is the critical angle? The critical angle is the angle of incidence formed, or the angle of incidence, the magnitude of the angle of incidence when the angle of refraction is 90 degrees. Okay, so a critical angle, or a critical angle is formed when the angle of incidence reaches a point where the angle of refraction becomes 90 degrees. And the critical angle is always measured when light is moving from a denser material to a less dense material. Okay, that's when the angle of refraction can be made to be 90 degrees. So I also drew something here, and I wrote my expression there, sine I over sine R. In our question, the light is moving from air into water, and when you're calculating the refractive index, we always take light to be moving from the less dense material. Even if it's moving in the other way around, we follow what we call the principle of reversibility when it comes to a movement of light. Okay, the principle of reversibility of light. Light will always take the same path, whether it's coming from this angle or the other angle. It will still make the same angles. Okay, when you set your source here, such that the angle here is 29, meaning the other angle is going to be 40. If you get your source of light, you set it here to create a 40 degrees, it will always make a 29 here, provided it's the same water and its density has not been tampered with and the air maintains its density. So since the angle of incidence is always measured in such a way that light is taken to move from a less dense material, we make the movement of light to be this way. And then since we understand that the critical angle is always in such a way that the angle of refraction is 90 degrees, so we make this one 90 degrees, which should be our angle of refraction. Then we simply make this angle of refraction our angle of incidence, because the refractive index is always calculated when light is moving from a less dense material. Allow me to go through that again. The critical angle is formed when light is moving from a dense material and into a less dense material, and the angle of incidence will be called the critical angle when the angle of refraction is 90 degrees. Okay, that is why I had to make this one 90 and this one my C. That's a symbol of the critical angle. Then coming back to the calculation of the refractive index, you always have to take light to move from a less dense material. So I reverse these again, okay, to have this small diagram here. So giving me this expression here, sine I over sine R. This is my sine R. Okay, but as you are defining the critical angle, if you followed me, I was saying the angle of incidence. But this one becomes my sine R because I'm taking light to be moving from a less dense material into a more dense, because I'm calculating for refractive index. So sine 90 is 1. Then sine C, which is my critical angle, is what we're looking for. The critical angle of water is what we're calculating for. So I have this expression here. I cross multiply. Okay, therefore I'm having sine C is equals to 1 over n. I've already calculated for my n, which is 1.33 in this question here. So finally I have this value here, 1 over this gives me this. Then I divide by sine on both sides. Then I simply raise this sign, or let me just say I multiply by sine inverse times this one, giving me 49 degrees. So for light moving out of water, to make an angle of refraction whose magnitude is 90 degrees, the angle of incidence from the water should be 49 degrees. Therefore that will be our critical angle for water. I move on to my third last question, which is question B7. Figure B7.1 below shows a 240 volt mains supply connected to a television set and 2 lamps. Okay, look at this connection: 40 watts, 40 watts, television of 120 watts, then a supply is 240. The live, the neutral. Okay, the live and the neutral, they have explained that for us. The first question there says the power supply to each lamp and television is 40 and 120 respectively when the switches are closed. Question A, calculate the total power supplied. Calculate the total power supplied. To calculate the total power supplied, I simply have to find my current. Okay, therefore find current in the branches. Okay, I find current in the branches. This is a parallel connection. This television is parallel to these bulbs, and these bulbs are parallel to each other, so I have to find the current here. I already have my voltage, but I need the current in here. Therefore current in a parallel section is may not be the same. So I first of all calculate for my current in the 120 watt, which is my television circuit here. I calculate by using the formula power is equals to VI. Therefore I make I my what? My subject. Power across the television is 120 over the voltage. Remember, voltage in parallel is the same. Voltage in parallel is constant, so there is 240 here and 240 in the bulbs. Therefore current here is 0.5. I do the same for the bulbs. Together they are both, and their total power is 80 watts. 80 watts over 240 gives me 0.33 amps. Therefore total current in the circuit is 0.83 amps. 0.83 amps. Then I come back here to calculate for the power in the circuit. Therefore power in the whole circuit, for me to calculate for power in the whole circuit, I simply go for this one here. I use the same formula. VI, which is 240 times 0.83, gives me 199.2 watts. That is my power in the total power supplied to the circuit. The next question there, which is total number of kilowatt hours of energy supplied to the circuit in 3 hours. In 3 hours. Total number of kilowatt hours. When you look at that formula there, that is actually a formula for energy. This is energy is equals to power times time. This formula comes from power is equals to energy over time, which is the same as work over time. Okay, so when you make E your subject, you're going to have power times time. And since we're talking about, this is talking about electricity, the cost of electricity or the unit of electricity in business. Therefore power or energy is sold in kilowatt hours. So power has to be in kilowatts and time has to be in hours. So the kilowatt here, or the energy, this is actually energy, is equals to power times time. Power in kilowatts and time in hours. So I divide the power I found here by 1000 to convert it to kilowatts. Then I multiply by 3 hours, which is already given here, which gives me 0.598 kilowatt hours, which is actually energy. Question 3 there, PD across the television set, which is PD is actually voltage across the television set. So PD across the television set is actually power, is this formula. So I make V my subject, then I do my divisions. It gives me 240. Remember I said voltage in parallel is always the same. Voltage in parallel is the same. Therefore, across this there's 240, and across this parallel section there's 240. But current may not be the same. That is why I had to calculate for current. I go to my second last question here. Figure B 8.1 below is a diagram showing a coil of wire wound on a soft iron core with the current flowing in the direction indicated by arrows. I've already placed my pause here. The first question says mark the north and south poles induced in the iron core. I had to check for the direction of current, and I had to apply my right hand grip. You can also use the perception view, where you imagine you're viewing it from this side or viewing it from the other side, but I used my right hand grip. I had to put my hand like that, then I grip it like that. So my fingers are pointing in the direction of current, and my thumb is pointing in the north. Current is going up, so within these coils the current will be moving upward, so I had to grip it like that. So this one is my north and the other one becomes my south. Show by arrow the direction in which a plotting compass needle would point when placed at point X. When placed at point X. Okay, so when it's placed at point X, a compass needle is actually has an arrow on one side, or it may be painted red. So this arrow is usually the north seeking pole. Okay, the north seeking pole or the north pole, and this other side is all the south seeking pole. So the south of the compass will be attracted to the south of the magnet. Okay, and the north of the compass is always attracted to the north of the magnet. On the compass, the north seeking pole, even on the magnet, the north seeking pole is called the north, and the south seeking pole is called the south. So this north pole of the compass will be attracted to the north, and this will be attracted to the south. So that will be the direction if you place your compass here. But if you're talking about a magnet, just a mere magnet, not a compass, then the perception will change. Number C, a beam of electrons flows through point Y in the direction perpendicular downwards into the paper. Okay, show clearly using an arrow labeled F the direction of the force exerted by the magnetic field on the electron beam. Okay, so the beam is going direct into the paper, and there's a magnetic field here. So how would you show the direction? Show clearly using an arrow labeled F the direction of the force exerted by the magnetic field on the electron beam. The electron beam would be deflected downwards. The electron beam will be deflected downwards. I'll look out for the video where I'm going to explain properly how the deflection would actually occur. Okay, how electrons or beta particles interact with a magnetic field. The last question there in section B is coming from the last topic in your physics, which is atomic physics. Phosphorus 32, therefore that's an isotope, can decay by emitting beta particles. What is the beta particle? My definition, though I didn't have much space there, is a negatively charged particle other than the proton that results after the decay of a neutron. From my definition, I've shown to say this is the other particle. Therefore, when a neutron decays, it decays to form a proton and the beta particle. The proton is positively charged and the beta particle is negatively charged. So other than this is descriptive, so you have to find a way of expressing this. A negatively charged particle other than the proton that results after the decay of a neutron. Therefore, two particles result. So whenever a neutron decays, the negative particle produced is called the beta particle. Number B, the proton number of phosphorus 32 is 15. State the new values of the proton and mass numbers of the nuclide. after decay, just after it emits a beta particle. Proton number is going to be 16, okay, because as from my definition here, a neutron decays to form a proton and a beta particle. Therefore, when it undergoes beta decay, the number of protons will increase by 1 if only one proton, one neutron underwent decay. Mass number will remain constant, because even if the neutron is converted to a proton, the number of nucleons wouldn't have increased. Question B2 there, write the decay equation for phosphorus 32 after emitting 2 beta particles. So meaning 2 neutrons will undergo decay, meaning 2 protons are going to be formed and 2 beta particles are going to be released, meaning the mass will remain the same, but the proton number will increase by 2. So P32 is here. It undergoes decay by beta to emit 2 beta particles, and it will result into a formation of another element, which is this one, with an atomic number of 17. The only element on the periodic table with atomic number 17 is chlorine. So the isotope that is going to be formed will be chlorine 32. Okay, so sometimes the symbol for beta particle is given as this, and sometimes it's given as that. Okay, as more like an electron, because they are both small and they're both negatively charged. My last question here in this video is as reads: phosphorus 32 can be used to prove that plants absorb phosphorus nutrients from the soil around them. State one safety precaution which should be taken into consideration when doing experiments with phosphorus 32. Avoid skin contact with sample. Avoid skin contact with sample. That would be one of my one of the precautions, because beta particles do have a little bit of an ionizing effect, and of course they might bring about ionization in our cells, which may result into mutations and other complications and even burns. So avoid skin contact. Of course, there are many others, like avoid bringing the sample close to your face. Wash your hands after using the being in the lab where there's such samples. Apart from that, work from a hood, work from a protected hood. Do not really come into contact with the sample. Basically, this is where I end with my video. Remember to like and share and subscribe. Look out for the questions. I'll deal with the questions one by one for section C, but for now I end this one. Bye bye for now.